Okay everyone, it's time for a little update to show you what I've been working on behind the scenes. Most of you know Tesla's turbine patents. Actually, this is from the British patent where they were both in the same patent, but the US patent office made him split it up into two, but actually they are related to each other. And so I have created both versions, the circular bore version and the volute version. As you can see, the circular one has been mounted there already with the speed sensor there. So we'll run that soon, but actually it all started with me purchasing this little Tesla turbine on Etsy. I paid $50 for it, and it kind of sucks because first of all, as you can see, if I spin the rotor, it stops almost instantly. Second of all, it's not true to the patent at all. Yes, it has two inlet ports, but the rotor doesn't have this. It just has circular holes in it, as you can see, instead of the actual shape of the rotor here, which I recreated, more accurately. Also, the number of discs is inaccurate. The shape of the inlet port is circular, even though we're going to need a converging nozzle. The exhaust is just here to the outside instead of where the actual exhaust was here. So I just started getting a little frustrated by that, and so I tried to build an upgraded version, and this is the result. Also, instead of these regular ball bearings, I'm using these high-speed dental bearings. They are ceramic and a hybrid ceramic actually, and they are incredibly tiny, and they can go up to 375,000 RPM. And just to give you a little taste, like if I hand spin this, it will keep spinning for about 30 seconds. So that's pretty impressive. They're very low friction and they don't need any lubrication. So yeah, that's what we're going for. This is a rotor. As you can see, it has 9 discs, just like in the patent. Here you see there's the 9 discs. The outside discs are, the end discs are a bit thicker to prevent warping. That's a design consideration Tesla came up with later, like after this patent, but still I implemented it here. You also see that the inside, the sidewall has these circular grooves that Tesla mentions in the patent as well, and that are missing from almost any replication I've seen. So you can see those mentioned here, number 13. Oh no, it's not number 13, number 26 actually. But anyways, so it's I tried to make a nice replication. I will show to you later how it performs. Also, this is what Paul Townley from the Nikola Tesla Research and Development Center came up with. If you look, like I said, they were in the same patent. The numbers are also just counting up, so it seems like they might have been part of a single machine. And if you look closely at the patent, and what Paul did here is he photoshopped them together, it seems like you can connect the center ports together. So that's exactly what I did as well. So here you have the center port. It comes out there. And then we have the volute here. Also has them come out there. And you can connect them together like that. And then it's just like in this drawing. So that's to test this two-stage setup. Right now I'm running it as a single stage because I'm still trying to figure out in general how these things work and how they perform before I go to the more complex two-stage setup. We also found some original drawings from Tesla. And what we see here clearly is this converging nozzle. So that's very important. So that's what I implemented as well. Not so much in this version. Here the inlets were way too small. So in this one has an improved inlet. It's a bit bigger, and it has the exact shape as in this drawing. This is another original drawing. a bit too small to see all the details, but it's cool to, this is actually the volute, as you can see, it gets smaller towards the center. Okay, so why don't we take this for a spin. I hooked up a multimeter. I'll set it to hertz. This is an optical speed sensor. So on the shaft, not sure if you can see it, but you know, it has a dark spot and then the shiny spot, and that's how it triggers. And as a compressed air input, I have this very wimpy duster, pressure duster to clean the inside of your computer with, but that's all I got right now. So let's see how far we can push this. So here's the RPM, or RPS actually, we're measuring hertz. Okay, I put my safety glasses on, let's go. Okay, it was a little tricky to hold it with just my left hand. There was a bit of back pressure as well, so that's why there wasn't a constant air input. But I believe the max we saw was about 370 hertz. So if we grab our little calculator and we do 370 times 60 to get the RPM, is about 22,200 RPM. That's not terrible. I gotten it up to 28,000 before when I had two hands to hold the pressure, the air pressure gun. But yeah, it's still not too bad. But you did hear the noise it made, and that's because the rotor is completely unbalanced as of now. It came out of a 3D printer, so it's not going to be perfect. It's actually printed with carbon fiber filament, so it is quite strong. I'm not sure at what speed it will explode. Of course, ideally you wouldn't use 3D printing, but this is just for learning. If you want to build a real model that can actually has proper performance, you should probably use aircraft grade aluminium or something. But anyways, yeah, so it's unbalanced, it makes a lot of noise. That's why it can't reach its maximum speed. Also because I have this wimpy compressed air source, of course. But after this I will be focusing on this patent, which is process of an apparatus for balancing rotating machine parts. So it's actually Nikola Tesla's dynamic balancing machine. And that's what I will be building next. So you have a casing for the rotor here. There is a lathe with a motor on it. This will actually be a Dremel in my case. And there's a speed sensor and there's a vibration sensor. As a vibration sensor, I will use my phone, an app on my phone, because it has an accelerometer in it. And yeah, I will be trying to balance it according to Tesla specifications and see if we can get it up to a higher speed that way. So thanks for watching. That's it for now, and I'll keep you posted on my next adventures. You can find all the 3D models in the description below.